Let's take a look at the following problem. We want to show that any isomorphism between two graphs maps each vertex to a vertex of the same degree. So let's go ahead and do a proof of this. What we mean is we're going to show in general that this has to hold. We saw in a previous video an example where we had a vertex of degree 4 in one of the graphs and there was no vertex of degree 4 in the other graph, so we couldn't find an isomorphism. In this video, what we're going to do is we're going to prove that this actually holds in general. So let's suppose there is an isomorphism. Suppose sigma is an isomorphism. I'm going to write an isom from G to H. And remember what an isomorphism is. It maps the vertices of G to the vertices of H as a bijection. It's one-to-one and onto. And anytime you have an edge in the graph G, it becomes an edge in the graph H after the mapping, and that's the only way you can get an edge in the graph H. So this is if and only if. Okay, so this is just to remind us always of what the definition is of an isomorphism. So here we have sigma. It is an isomorphism from one graph to another graph. What we want to do is show that each vertex of G gets mapped to a vertex in H which has the same degree. So what we're going to do is we're going to take any vertex of the graph G. And it has some degree. I don't know what its degree is, but let's say that R is the degree in the graph G of vertex V. Okay, so it has degree R. We're going to let the neighbors be U1, U2, up until UR be the neighbors of V in G. So in other words, within the graph G, we have some vertex V, and it's any vertex. It has some neighbors, and those are U1, U2, and keep going until you get to UR. Okay, so we know that VUI is an edge in the graph G for I equals 1, 2, all the way up to R. That's what this tells us because these are the neighbors. And these are exactly the neighbors, so V doesn't have any other vertices that are adjacent to it. Okay, because we have some isomorphism, after we map over to, if we apply the isomorphism sigma, well, what's going to happen? We're going to end up with this vertex V, which is now sigma of V. This is all inside the graph H. And because this is an isomorphism, we know that there will be an edge sigma V, sigma U1. Sigma U1. Because VU1 is an edge of G, so sigma V, sigma U1 is an edge of H. And that same thing holds for sigma U2, and you keep going until you get to sigma of UR. All of these are edges in the graph H. And how do we know? So actually, first of all, what does this tell us? What this tells us is that the degree of, in the graph H, of the vertex sigma V, remember that's just a vertex, its degree is at least R, because it has these R neighbors. Now, how do we know it doesn't have some other vertex here that it's adjacent to? How do we know that there isn't something like that? Maybe we should call this sigma W, right? Well, if there is a sigma W, which is a vertex in the graph H, with sigma V, sigma W being an edge in the graph H. That's really what this picture is showing. We want to show that this cannot happen. If that does happen, well, then VW would have had to have been an edge in the graph G because of the definition of sigma being an isomorphism. You would have had to have had another vertex out here which was incident with V, and this was not the case I'll just draw that in red or orange. This is not the case because these are all the neighbors of V. So this cannot be the case. This is not true. So we tried to say, well, if the degree of this vertex in graph H is bigger than R, well, what happens? We run into a contradiction. So that means we conclude, so the degree in the graph H of the vertex sigma V is also equal to R. And thus, V gets mapped to sigma of V, which has the same degree. The same degree as V. So that's another thing that you can do when you're checking if something is going to be isomorphic to another graph. The degrees, as if you look at the degrees of all of the edges of the graph, they have, sorry, not all of the edges, all of the vertices of the graph, they will have to agree. And we've just done exactly what we set out to do. We showed that if we have some vertex V in the graph G, which has R neighbors, then whatever we map it to in H, that new vertex will also have R neighbors. Okay, so hopefully that all made sense, and you can also review the simple example we did of a concrete example when we had degree 4 in one graph and no vertex of degree 4 in the other graph, which was in a previous video.